Before we begin, take a moment to settle in. This is not a quick explainer or a list of facts. It is a long journey through ideas, machines, and decisions that quietly reshaped the modern world. What you are about to hear is the story of how computing escaped the room it was locked in and spread everywhere. How an abstract symbol in an engineer's diagram became the invisible infrastructure of daily life. This story moves slowly on purpose because the cloud did not arrive all at once. It accumulated. It layered itself over decades of ambition, fear, invention, and compromise. If you stay with it, you will start to see familiar technology differently. Not as magic, not as inevitability, but as a human construction, fragile, powerful, and unfinished. If you find yourself drawn into this history, if it changes how you think about the tools you use every day, consider supporting this work. Share it with someone who cares about technology beyond headlines. Subscribe if you want to continue this series and explore what comes next. Long-form storytelling like this survives only when people choose depth over speed. Your attention is what makes it possible. And now, when you are ready, let's begin. Look up. Not at the sky, but at the invisible infrastructure that surrounds you every day. The thing we casually call the cloud. It is not weather. It is not vapor. It is a set of decisions made over decades that turned computing from a scarce industrial resource into something that feels as ordinary as running water. It holds our photos and our work, our medical records and our friendships, our entertainment and our money. It runs the quiet machinery behind deliveries, loans, maps, messages, translations, recommendations, and alarms. It has become the nervous system of modern life, and in a more subtle way, it has begun to influence how we think, what we remember, and what we expect the world to do for us. Because the cloud feels ambient, it is easy to imagine it is new. Something born with smartphones, something that arrived fully formed with streaming video and social feed. But that feeling is an illusion created by a final layer of polish. The idea is older than most of the people using it. The dream of computing as a utility goes back to the earliest days of electronic machines, to a time when computers were rarer than diamonds, heavier than construction equipment, and treated less like tools than like institutions. To understand how the cloud became inevitable, you have to begin in the era when computation was not personal and not intimate. It was heavy iron and guarded access. It was a calendar and a queue. It was the mainframe. In the 1950s, a computer was an installation. The famous names of that age sound like battleships, because, in a sense, they were. UNIVAC, the IBM 700 series. These machines consumed enormous amounts of electricity and produced heat that had to be managed like an industrial process. They lived in dedicated air-conditioned rooms. People called them glass houses because the hardware was visible behind windows like an exhibit, and because access was controlled. There were technicians in white coats, not because it was fashionable, but because the work was more like lab maintenance than office work. Cables, tape drives, card readers, and cabinets that looked like furniture designed by an engineer with no time for beauty. A single system could cost millions of dollars, which meant the organizations that owned them treated them as strategic assets. Universities, large corporations, government labs. If you were not inside those walls, the computer might as well not exist. Even inside the walls, the way people used these machines was nothing like the experience we now take for granted. It was batch processing. You did not sit at a keyboard and explore ideas in real time. You prepared your work in advance, you submitted it, and you waited. Programs were written onto punch cards, physical cardboard, with holes that represented instructions. A scientist or engineer might carry a stack of cards like a fragile deck of logic. You handed it to an operator who fed it into the system when your turn came. Your job ran when the machine reached it in the queue, and then you received output later, often on paper, sometimes hours or days afterward. For the humans, this was maddening. A single typo might invalidate an entire run. Imagine waiting overnight to learn that you misspelled a variable on card 42. But the deeper problem was not the inconvenience to people. It was the waste of the machine. Even early processors were fast compared to the mechanical devices that fed them. Card readers and tape drives were slow, and while the machine waited for data, the expensive electronic heart sat idle. The organization had paid for a racing engine and then forced it to spend most of its time waiting at the curb. Scarcity was not just a matter of price. It was a matter of inefficiency. Computing could solve enormous problems, but it could not be used casually. It was reserved for the most critical work: nuclear physics, ballistics, census data, large-scale accounting. The computer was a weapon, a calculator, a bureaucratic tool. It was not yet immediate. And yet, inside that landscape of scarcity, there were people who could see past the metal. They saw a future where the machine would not be a shrine behind glass, but a shared resource, accessible, flexible, and woven into daily life. Two names stand out, not because they were the only visionaries, but because they articulated the shape of what came next with unusual clarity. John McCarthy and Joseph Carl Robnet Licklider, known as J.C.R. Licklider. McCarthy, one of the central figures in the early history of artificial intelligence, made a statement in 1961 that still sounds fresh because it points directly at the core economic idea of the cloud. He suggested that computing might someday be organized as a public utility, not a luxury product, not a piece of private machinery, but a service available through a network, paid for according to usage. The analogy mattered. You do not keep a power plant in your basement. You plug into the grid. You consume electricity when you need it and stop paying when you do not. The complexity and maintenance of generation and distribution are handled elsewhere by specialists, and the user experiences the result as a simple interface, an outlet in the wall. If you follow that logic, you do not need to own a computer to compute. You need access. You need a way to request processing and storage the way you request electricity with reliability and predictability. To people living among mainframes that required their own rooms, this sounded like science fiction. But it was also a practical proposal. It implied a model for making computation cheaper and more widely available by pooling resources. Around the same time, Licklider was developing a vision that was less about accounting and more about the relationship between humans and machines. He wrote about man-computer symbiosis, the idea that computers should augment human intelligence in real time. He was not satisfied with faster batch jobs. He wanted interactive computing, a partnership. He imagined a world where people could access data and processing instantly from anywhere, a networked environment that would connect minds through machines. He famously joked about an intergalactic computer network, and the joke landed because it captured the scale of his ambition. He was imagining not a single system, but a connected ecology of systems. His visions were not just predictions, they were challenges. If you accept the idea that computing should be a utility, and a medium, you have to confront what the machines of the era could actually do. Batch processing could not deliver interactivity. The mainframe, as a single job machine, could not create the illusion of personal access. And that is why the next breakthrough mattered so much. The thing that would make the utility model practical for the first time was time-sharing. Time-sharing begins with a simple observation about speed mismatches. The processor is faster than any human. A person types slowly, thinks slowly, reads slowly. If you give the processor to one person at a time, you waste it. But if you let many people share it, the processor can switch between them so quickly that each person experiences the system as responsive. The machine gives each user a slice of time, then moves to the next, then back again, cycling rapidly. In the era when most people still thought of a computer as a single-minded device doing one job at a time, this was a conceptual leap. It treated computing as a pool of capacity that could be scheduled, partitioned, and allocated dynamically. The magic of time sharing was psychological. People sat at terminals, sometimes miles away from the central system, and typed commands. The machine responded quickly. It felt personal. It felt interactive. Behind the scenes, the mainframe was juggling dozens of users, switching context in milliseconds. The illusion was that each person had a dedicated machine. The reality was resource pooling. This is the first practical ancestor of the cloud experience. Many users sharing a central resource through an interface that makes the sharing invisible. At MIT, with funding from the United States Defense Research Apparatus, this idea turned into a real system. Project MAC, Mathematics and Computation, built the compatible time-sharing system, CTSS. It was a large-scale demonstration that computing could be delivered as a service inside an institution. Researchers could log in from terminals across campus. They could store files centrally. They could share code. They could send messages. Those details matter because they reveal how early the shape of modern networked life. Central storage, shared tools, electronic communication, remote access. It was not the internet yet, but it was a proto-cloud inside a single ecosystem. Time-sharing proved the utility model could work locally. But a utility is only truly transformative when it scales beyond a single building. Electricity reshaped society because it could be distributed. Telephone networks changed culture because they connected people across distances. If computing was to become a utility, it would need a network. The push to connect computers across distances was driven by both curiosity and fear. The Cold War created an intense interest in communications systems that could survive disruption. The defense establishment wanted command and control networks that could endure the unthinkable, including nuclear attack. A centralized network with a single point of failure was unacceptable. The idea of a distributed network where information could route around damage became more than an academic concept. It became a strategic desire. Licklider's role at ARPA, the Advanced Research Projects Agency, gave him influence over funding decisions that shaped the future. His successors, including Ivan Sutherland and Bob Taylor, carried the networking vision forward. The result was ARPANET, a project that sounds modest in hindsight but required solving problems that had never been solved at that scale. The central issue was interoperability. Different computers from different manufacturers spoke different internal languages. They had different operating systems, different assumptions, different hardware interfaces. Connecting them was not like plugging two identical devices together. It was like trying to make two people converse fluently while each speaks a language the other has never heard. The solution involved creating specialized machines that would sit between systems and handle communication. Bolt, Beranek, and Newman, a small consulting firm, won the contract to build these devices. They created the Interface Message Processor, the IMP, a predecessor of the modern router. By the end of 1969, the first nodes of ARPANET came online at UCLA, Stanford Research Institute, UC Santa Barbara, and the University of Utah. The famous first attempt to send a message from UCLA to Stanford only got as far as the letters L and O before the system crashed. But even in failure, the moment mattered. A message had traversed a network linking two distant computers. The metal beasts had been connected. The idea of computing as a utility had been articulated. Time sharing had created a way to pool resources and deliver interactive access. A network was emerging that could connect those resources. But it would be a mistake to imagine the cloud was born at that point. The systems were still fragile and expensive. Access was still limited to governments and universities. The dream existed, but the world was not ready to live inside it. The 1970s opened with a web of connections that was real but chaotic. ARPANET worked, but it was experimental and exclusive. If the 1960s were about imagining the network, the next 2 decades would be about building roads, standardizing the infrastructure so data could travel between worlds, not just between labs. This was the era of protocols and pipelines, where the most influential inventions were not glamorous hardware, but rules, agreements, and design philosophies. The fundamental problem was a Tower of Babel. If you wanted a global network, you needed a universal language for data movement, something that could sit above the specifics of individual machines. The answer came from Vint Cerf and Bob Kahn. In 1974, they published the work that proposed Transmission and Control Protocol and Internet Protocol, TCP and IP. It was not a device you could photograph. It was a way of thinking about communication. The genius of TCP and IP was that it embraced packet switching. Data would be chopped into small packets, labeled with addresses, routed through the network, and reassembled at the destination. The network could be decentralized. Packets could take different routes. The system could be robust against failure. Most importantly, the protocols did not care what kind of hardware you used. They created a layer of abstraction that allowed heterogeneous networks to interconnect. A universal language, a digital Esperanto. While long-distance networking was gaining its grammar, a separate revolution was occurring at the scale of buildings and campuses. At Xerox PARC in 1973, Robert Metcalfe developed Ethernet, a way to connect computers within a local area at high speed. Before this, moving data inside an office could mean physically carrying disks from one machine to another, the so-called sneakernet. Ethernet turned buildings into networks. It made connectivity a default expectation inside organizations. It created the local area network, the LAN, which would become the basic unit of corporate computing. When LANs connected offices and TCP and IP connected networks, a new architecture solidified, client-server. In this model, centralized servers held data and applications, while clients, less powerful machines, requested services. This pattern is a direct ancestor of cloud computing because it separates where computation happens from where the user experiences it. The server becomes a vault. The client becomes a window. It also creates the possibility of centralized management, upgrades, and security, while users operate through relatively simple devices. But just as networking was maturing, the hardware landscape shifted in a way that seemed to challenge the utility model. The personal computer revolution moved computing power from glass houses to desktops, Apple II, IBM PC. Suddenly, individuals and small businesses could own machines. This democratized computing, but it also re-isolated it. Early PCs were islands. They held data locally. They ran software locally. Without networks, each machine became its own world. That fragmentation created a hunger for connection. People wanted email and file sharing and access to information. In response, consumer-facing online services appeared. CompuServe, The Source, Prodigy, AOL. These platforms offered a taste of centralized services over a network. News, weather, stock quotes, chat rooms, email. But they were walled gardens. You could not freely communicate between them. Each was its own private cloud before the term, a closed ecosystem where the provider controlled the experience. The Internet, as a truly interconnecting system, needed a moment of standardization. And that moment came on January 1st, 1983, a date often called Flag Day in the networking world. On that day, ARPANET switched from its older protocol to TCP and IP. It was a risky transition because it required coordinated change, but it worked. Networks could now interconnect more easily. The network of networks was born. The Internet became more than a defense project. It became an infrastructure. During the 1980s, companies began to compete for dominance over this networked computing world. Sun Microsystems, founded in 1982, coined a slogan that sounded like a provocation. The network is the computer. The phrase mattered because it reframed the unit of value. Not the standalone machine, but the connected system. A single computer without a network was limited. A computer embedded in a network could access shared resources, distributed services, and collective power. At the same time, businesses began to centralize their own infrastructure into what became known as data centers. Servers moved out of broom closets and into dedicated facilities. Rows of racks, raised floors for cooling, backup generators, controlled access. These were fortresses of computation. They were expensive and rigid. Buying a server meant procurement cycles, delivery times, installation. Scaling meant planning. It was the opposite of elastic. A different kind of frustration emerged. Scientists and researchers struggled to share information across systems that were still not user-friendly. The internet existed, but it was mostly command line and difficult for non-experts. At CERN, Tim Berners-Lee saw a missing layer. He proposed a way to link documents across the network through hypertext. In 1989, he outlined what would become the World Wide Web. The web is not identical to cloud computing. The web is an interface. The cloud is an operating model for computation and storage. But the web would become the front door through which the public entered the networked world, and eventually, the cloud. It made the internet navigable. It turned a technical network into a medium for culture, commerce, and identity. And in the background, a small symbolic detail was quietly forming the very word we now use. Telecommunications engineers designing complex switching networks needed a shorthand and diagrams. They could not draw every switch and route, so they used a simple cloud shape to represent the messy network in the middle. Cloud meant abstraction. It meant the details were hidden. It meant what happens inside is the provider's responsibility, not the user's. The symbol came before the marketing. The metaphor emerged naturally because the network had already grown too complex for any one person to map. By 1990, the stage was set. Standards for data movement, local networking, centralized servers, an emerging web interface, and the conceptual symbol of abstraction. But the economic model was still ownership. If you wanted to build something online, you bought machines, you built a data center, you hired people. It's the future. Then the digital levee broke. The 1990s were the decade when the internet stopped being a research network and became a cultural force. The web browser unlocked the network for ordinary people. From text commands to pages, images, storefronts, and communities. It became a gold rush, a frantic explosion of optimism, speculation, and genuine invention. And within that chaos, cloud began to take its literal shape, not yet as a product category, but as a necessity born from pain. Before it was a buzzword, the cloud remained a diagram symbol, a way to hide complexity. But the very act of hiding complexity turned into a philosophy. If the network is too complex, the user should not be forced to understand it. The service should work. The interface should be simple. The provider should absorb the complexity. This idea is not a luxury, but a requirement for scale, becomes the soul of cloud computing. The 1990s also saw a massive infrastructure boom driven by anticipated demand. Telecommunications companies and new global players borrowed huge sums to lay fiber optic cables across continents. They were trenching the world, building pipes for a future that investors imagined would arrive immediately. Fiber promised enormous bandwidth. It was physical optimism laid into the earth and sea. But for companies trying to build internet businesses, the day-to-day reality was harsh. If you were a startup with a great idea in 1997, you faced the capital expenditure wall. You could not simply rent compute capacity. You had to buy servers. You had to rent space in a data center. You had to hire network engineers. You had to install cooling and power. You had to plan for scale before you knew if anyone cared about your product. The lead times were slow. The costs were heavy. Infrastructure was a bottleneck. This created a particular kind of tragedy that became common in that era. If your site suddenly got attention, you crashed because you could not add servers fast enough. If you overbuilt, you burned money on idle hardware. The risk was structural. Success could destroy you, and so could caution. The internet wanted speed. The infrastructure demanded planning. Enterprises faced their own version of the problem. They needed to connect branch offices securely over the chaotic public internet. One partial solution was the Virtual Private Network, VPN, which used encryption to create secure tunnels. This mattered not just for security, but for the concept of using shared public infrastructure to build private, controlled environments. It was an early step toward the cloud's promise that you can carve private spaces out of public networks. In academia and science, another precursor developed: grid computing. Scientists needed immense processing power for climate models, simulations, and sequencing. Rather than rely on one supercomputer, grid computing linked many machines to act like one. The public saw a friendly version of this idea in projects like SETI at home, where millions donated idle cycles through screensavers to analyze radio telescope data. Grid computing proved you could decouple processing power from physical location, but it was mostly suited for batch jobs. It did not yet translate cleanly into interactive commercial services. By the end of the decade, the dot-com boom reached fever pitch. Investors poured money into anything that promised online growth. The motto became, "Get big fast." Companies built infrastructure for millions of users who did not exist yet. Telecom firms laid far more fiber than demand required, creating dark fiber, unused bandwidth waiting in the ground. Data centers were built as monuments to anticipated traffic. The world was awash in excess capacity, purchased with borrowed money and inflated stock prices. Then the correction came. March 2000. The Nasdaq peaked, wobbled, and crashed. Trillions in market value evaporated. Data centers built on speculation sat half empty, lights blinking over rows of unused servers. Dark fiber lay dormant under oceans and cities. It looked like the end of the dream, like proof that the internet had been mirage. But the crash did not destroy the underlying desire for connectivity. It cleared the brush. It left behind something crucial. Vast amounts of high-quality infrastructure suddenly available, and a market desperate for a business model that could use it efficiently. The crash forced a reckoning. The old model where each company built its own private data center and guessed its future capacity needs was unsustainable and risky. The world needed a way to treat computing capacity as flexible and shared. And in an era when money was suddenly harder to find, the appeal of renting rather than buying became obvious. One of the most important shifts of the early 2000s happened not at the infrastructure layer, but at the application layer, where a company made a radical claim about how software should be delivered. In 1999, Mark Benioff, a former Oracle executive, founded Salesforce. His idea was simple and heretical. Enterprise software at the time meant buying box products, installing them on your own servers, paying consultants to customize them, then paying for maintenance and upgrades. It was expensive, slow, and painful. Benioff declared the end of software, meaning the end of software as a product you own. Instead, software would be a service you rent. You would not install it. You would access it through a web browser. The application would live on the provider's servers, and the provider would manage upgrades, security, backups. Customers would pay predictable subscription fees. This was software as a service, SaaS, the first widely recognized mainstream version of the utility model from the end user's perspective. SaaS proved something psychologically important. It proved that businesses would trust mission-critical applications to remote servers over the internet, as long as the experience was reliable and the economic model made sense. It shifted costs from heavy upfront spending to ongoing operating expenses. It did not yet solve the deeper infrastructure problem for developers who wanted raw compute power, but it proved the market would accept the idea that the software and data could live elsewhere. At the same time, inside a company that had survived the dot-com crash, a different transformation was unfolding. Amazon was growing fast, shifting from an online bookstore into a broad commerce platform. But internally, Amazon's technology infrastructure was a mess. Teams building features needed servers, storage, databases, and they often built their own versions from scratch. There was duplication everywhere. Provisioning was slow. Growth was being throttled by the physical reality of infrastructure. Around 2002, Jeff Bezos issued a directive that would later become famous as the API mandate. The message was brutal in its simplicity. All teams must expose their data and functionality through service interfaces. No more direct connections, no more backdoors. Everything would be modular. Everything would be accessible through API. The mandate was enforced with threats that were not gentle. It forced Amazon to re-architect itself from a monolith into a collection of services. This internal restructuring mattered because it created reusable building blocks. A team could build a world-class storage system for Amazon's needs. Another could build compute management. Another could build databases and messaging. And as those internal systems matured, a realization formed inside the company. These were not just internal tools. These were products in waiting. Around 2003 and 2004, a small team led by Andy Jassy began to look at Amazon's internal infrastructure and see it differently. Amazon had become expert at running computing resources at massive scale, handling peaks in traffic, managing storage, building resilient systems. Most companies did not have that expertise. Most developers could not afford to build it. So the question emerged quietly at first: if we need this, do others need it too? Why should a developer in a dorm room or a startup in a garage buy servers and rent data center space? Why not rent them the infrastructure through APIs, the way Salesforce rented software? For that idea to work economically, virtualization Virtualization allows a single physical server to be sliced into multiple isolated virtual machines. Instead of giving a customer a whole physical box, you can give them a fraction securely separated from other tenants. It makes resource pooling more efficient. It makes it possible to allocate capacity dynamically. VMware commercialized virtualization in a way that made it mainstream in enterprise environments, and it helped normalize the idea that the machine you use may not be a physical machine at all. By the end of 2005, the ingredients were aligned. Cheap infrastructure from the crash, proof that users would accept services delivered over the internet, virtualization to make sharing efficient. And inside Amazon, internal services robust enough to become external offerings. Then in 2006, the ground shifted. Amazon released Simple Storage Service, S3, and it sounded almost comically boring. Storage buckets accessible through an API. But the simplicity was the point. Developers could store data for pennies without contracts and hardware. It was instant. It was elastic. It treated storage as a commodity, not a project. A few months later came Elastic Compute Cloud, EC2. This was the moment the utility vision became real for a broader developer audience. EC2 let anyone rent virtual servers by the hour. You could spin up one server to test an idea or hundreds to handle a spike, then shut them down when you were done. You paid for what you used. There was no waiting for delivery, no installing racks, no negotiating leases, just an API call and a credit card. The psychological impact was hard to overstate. Until then, building a technology company required dealing with physical reality, space, cooling, power, shipping. Suddenly, infrastructure became software. A startup could build and scale without owning servers. The barrier to entry collapsed. Experimentation became cheap. Failure became less expensive. That changed the culture of innovation. It also changed the economics of venture capital. Investors no longer needed to fund heavy infrastructure purchases before a product existed. They could fund prototypes. They could fund iteration. Could scale only when demand proved itself. A new generation of companies grew in this environment, often described as cloud native, because they were born without data centers. Dropbox, Airbnb, and many others built on rented infrastructure. In some cases, the cloud provider's services were not just a platform, but a core dependency. The other tech giants were caught off guard. Microsoft and Google had enormous infrastructure, but they used it internally for their own products. They had not fully embraced the idea of renting it out as a public utility. Google responded with App Engine, which was technically impressive, but it was restrictive. It required developers to write code in Google's preferred way. AWS, by contrast, offered raw primitives first. Virtual machines, storage, networking. It said, do what you want. As AWS grew, the term cloud computing escaped engineering circles and entered public language. But with visibility came confusion. Legacy companies began to attach the word cloud to everything. Products that were essentially traditional hosting or managed servers were suddenly rebranded as cloud. Cloudwashing became common. The term became a marketing flag for modernity, even when the underlying model had not changed. Still, the economic gravity was undeniable. And then another crisis arrived that accelerated cloud adoption in a very different way. The Great Recession of 2008 made organizations cautious. Budgets tightened. Capital expenditures became harder to justify. Building a data center was a heavy bet. Renting infrastructure as an operating expense, flexible and cancelable, became attractive. Ironically, the economic shock that could have slowed technology investment instead pushed companies toward cloud because cloud was cheaper to start and easier to adjust. OS expanded rapidly, adding databases, content delivery networks, monitoring, identity systems, messaging queues. The console began to feel less like a simple service and more like the cockpit of an operating system for the internet. The cloud was no longer just infrastructure rental. It was a menu of building blocks for new digital world. At the same time, a cultural device arrived that would become symbiotic with the cloud, the smartphone. The iPhone launched in 2007. The App Store followed in 2008. Mobile apps needed backends. They needed storage, authentication, synchronization, notifications. The smartphone was a screen and a sensor. The cloud was the brain that made the screen useful. The rise of mobile and the rise of cloud reinforced each other. The more people expected instant access everywhere, the more services needed centralized, scalable infrastructure. Netflix offered a dramatic proof of the cloud model's power and risk. After a major database corruption incident disrupted DVD shipping operations for days, Netflix decided to move its infrastructure to the cloud and rebuild its streaming platform there. It was a gamble, especially because also entering video. Trusting a competitor to host your business sounds irrational, but Netflix did it because the cloud offered resilience and scalability that would have been extremely costly to build alone. Netflix became a showcase for cloud-native architecture, and its success made the cloud feel not just possible, but inevitable for large consumer services. And public cloud was no longer a toy, it was a force. Amazon had a multi-year head start and a growing feature gap. But the giants began to wake fully. Microsoft announced Azure, and slowly, painfully, began to accept that the future of computing might not center on the Windows operating system, machines you own. The operating system of the future might be the internet itself. If Microsoft did not own the cloud layer, it risked becoming irrelevant. As the new decade began, the cloud wars took shape. What had started as a clever infrastructure product from an online retailer became the foundation for over the landlordship of the digital world. Amazon was in the lead. Microsoft and Google had the resources to compete. The stakes were enormous because the cloud is not just a product, it is leverage. Whoever hosts the world's data and workloads gains influence over the pace of innovation, software, and the structure of modern business. Microsoft entered the decade facing an identity crisis. For decades, its dominance came from the personal computer and enterprise servers running Windows. The cloud threatened to make the operating system a commodity. If applications live in browsers and containers, underlying OS is. Microsoft's early Azure approach leaned toward platform as a service, trying to pull developers into a Microsoft-specific model. Adoption was limited because developers wanted flexibility. They wanted the cloud to be infrastructure first, not a constraint. Inside Microsoft, this created cultural conflict. The company had to choose between protecting the legacy business and embracing the future. The pivot required humility. It required supporting Linux. It required treating Windows as one option among many. That change was not just technical, it was psychological, a shedding of an old worldview. Google had a different problem. Internal infrastructure, including container-based systems and cluster management, that were far ahead of what most companies could build. But Google believed the advantage was in keeping that technology secret. Its public cloud offerings arrived late, and developers would adapt to Google rather than the other way around. When Google eventually launched a more general compute service, it was entering a market where AWS had already become the default. From 2010 to 2014, the cloud wars became an arms race. AWS launched services at a blistering pace. Azure expanded aggressively. Google cut prices and tried to differentiate through data and machine learning. Price wars erupted. Feature parity became a battlefield. The providers built more regions, more availability zones, more redundancy, more tools. The cloud began to look like an endless library of services, each with its own learning curve. But the real prize was not startups. Startups were already in. The prize was the enterprise. 500 budgets. Banks, healthcare providers, governments. These organizations had legacy systems and strict compliance requirements. They were cautious. They feared security breaches. They feared losing control. They also had inertia. Decades of processes built around on-premises hardware and long procurement. They could not simply move everything to the public cloud overnight. This tension birthed the hybrid cloud concept. Not a full migration, but a bridge. Keep sensitive workloads on premises. Connect them securely to cloud resources for new applications, analytics, and burst capacity. Adopt cloud without abandoning legacy infrastructure. It was also a strategic advantage for Microsoft because Microsoft already dominated on-premises enterprise environments through Windows Server and identity systems. Microsoft could sell a narrative of continuity. Your existing world can connect to the new world, and we can. As enterprises adopted cloud gradually, another fear grew. Vendor lock-in. If you build everything on one provider's proprietary services, leaving becomes expensive and painful. The fear was not irrational. The more you use specialized managed services, the more your architecture becomes entwined with that provider's ecosystem. That fear fueled an movement. OpenStack. Launched in 2010 with support from NASA and Rackspace, OpenStack promised an open cloud operating system that anyone could deploy to build an AWS-like environment in their own data center. The dream was the Linux of the cloud, a common platform that could prevent monopoly control. Immense hype and support from many companies that did not want Amazon to dominate. But OpenStack struggled. The problem was complexity and coordination. Building a cloud platform is hard, and doing it by